Thanks very much for agreeing to give us this impromptu seminar, Matthew. Seminar from Matthew Dolan, who is visiting from the University of Melbourne. And we're very informal, so
very good. Good. Yeah, lovely to be back at IOS again. I was here in May for the conference, and this is basically the seminar version of the short talk that was given then. And yeah, I'm just passing through, so I'm disappearing after this. This is not actually a work trip. Back to see family, but I got suckered in. Can't avoid it. So yeah, I'd like to talk to you today a little bit about my work on dark matter related physics, although most of what I'm going to be talking about is more like atomic physics than astrophysics or any of the usual dark matter kind of stuff. This is based on 2 papers written with collaborators all at the University of Melbourne. So these, I'm not going to go through everybody, but these people are basically this is at King's College London. Harry here is relativistic atomic theory, which is important to everyone else, like a particle physicist who is a student or a postdoc or faculty. Okay, so the main motivation for thinking about the kind of stuff that we've been thinking about for the past few years is that dark matter exists and we don't know what it is. All the evidence we have for the existence of dark matter is astrophysical or cosmological, coming from galaxy rotation curves or cluster dynamics in the top 2. There's CMB, so the positions, in particular the ratios of these CMB power spectrum feeds are telling us that there's dark matter near the universe. And if you put all this together, you know that there's like nothing to say about that. The dark matter is sort of something like 80% of the matter. And my own interest is, what is the particle physics of dark matter? Everything else. Everything is some kind of a field or particle, and what is the dark matter? How did its relative density come to be achieved? All this kind of stuff. So it's hard to get a handle on that from astrophysics measurements, and so it'd be really nice if there's some way that we could understand the particle nature of dark matter with terrestrial experiments. And so what I'll be talking about today is related to direct detection. So direct detection is where, let's say, the dark matter is particles for the purpose of this talk, which is true. It can also be more like wave-like stuff at lower mass ranges, but that's not what we're talking about today. So the idea there is that some particle dark matter comes in, from the Milky Way halo, and it will scatter, or could scatter, off what we call normal matter, so stuff that's in the standard model. And if you build a sensitive enough detector, then you can detect the recoil of the standard model from that dark matter standard model scattering. Okay, so this is what direct detection is. And so this is an idea that goes back to the 80s, but has really hit its stride, in a sense, in the past 15 years with the development of large-scale detectors and also the development of more sensitive detectors, because you really want to be able to detect small energy depositions from dark matter scattering. Okay, so
just behind that, other than wishful thinking, what is the evidence that?
So the evidence is particle. That it is which, a particle or?
That it is a particle, yes.
Well, none. Yeah. If you want actual evidence, no. It could be primordial black holes. I mean, there's a small window for that where I think it could still be primordial black holes, asteroid mass primordial black holes. It could be axions or ultralight stuff with a mass of 10 to the minus 15 eV, and then it's not particles, just because the occupation number is so high, you treat it like a classical field. So that is, the mass range on this stuff is very, very wide, but it is in this sort of window here, so it's around the scale where we know that direct detection can be sort of sensitive.
And what would be the upper mass window?
For which?
For
particles. Yeah, well,
for dust, this dust.
That's a good question. Yeah, so people have traditionally considered around 100 TeV based on unitarity arguments, but that's just for freeze out, for thermal freeze out. So if you go beyond freeze out, then you can extend that to much higher things if you have gravitational production, for example, or it depends how creative you're willing to be as well, right? You could have particle, imagine that the dark sector is something like QCD, but without the existence of electromagnetism, so that you can build arbitrarily large nuclei. Right, so nucleosynthesis, dark nucleosynthesis occurs, but it can occur for a long time. So instead of there being a maximum nuclear number, atomic nuclear number of 100, like in our sector, it could be 10 to the 15 or 10 to the 10 or something like that. You can engineer that, right? So you could then have sort of dark blobs, and they're not fundamental. They're like dark nuclei, but they have an atomic mass number, an atomic number of 10 to the 10 or something. And then you can get close to you can probably get up to like close to 10 to the 10 or 15 GeV then, and it's still kind of a particle, but not necessarily like a fundamental particle in the same way. As you get to heavier masses, you have to usually do some kind of gravitational correction through inflation or stuff like that. But it's also a large window there. Yeah. The problem there, if you want to detect it, is that you know the mass because we know the energy density, so then the number density is going to be really, really small, and so the number of those things passing through the Earth just drops, inverse of mass, right? So the chance that you have detecting that terrestrially is then not very good at all. So there's a sort of a sweet spot where the number density of this stuff is quite reasonable, and that's what causes this uptick. Right? So this thing keeps going like that, and that's just because as you increase the mass, the number density is going down, and you expect the number of events in your experiment will also go down, so you sort of worsen. So there's this like sweet spot here where from the scattering, the energy at the deposition is large enough to detect, and the number density is very large enough as well. Of course, the original, as you will know, motivation for these things was from sort of the hierarchy problem for thinking about this particular mass range. But there's lots of theories like SUSY that do give you candidates which are of order the literally. At this stage, though, I think the community is. I don't know. I'm happy to talk if you're happy to listen. Yeah. The community, even when I was a young PhD student, like 15 years ago, the community was still very focused on this.
This is the WIMP miracle.
The WIMP miracle before the LHC. And then the LHC has not turned up supersymmetry, obviously, or anything that looks like it's going to solve the hierarchy problem if you buy into that. And consequently, the particle physics community has become much more open-minded as to what dark matter could be, in a very healthy way, I think. And it is now exploring as far as it can in that direction, and as far as it can in this direction, for both experimental and theoretical, I think. So the motivation to look in a particular place is now more like personal interest, if you like, what you like to think about, and also, have we looked there? Because there is a feeling that if we can look, we probably should, away from the traditional lampposts. A lot of the work in the community, coming back to what I actually want to say in the talk, in the past 5 or 10 years, has been trying to figure out how can we look down here. By exploring the experiments that we have, designing new experiments, we have sensitivity to very, very small energy depositions, that kind of stuff, quantum sensors. Okay. So this is from the American snow mass process. This is a sort of a big summary of where we are with their detection at the moment. So this is the dark matter nucleus cross-section, the dark matter mass. So the most sensitive that we can get at the moment, these are tiny cross-sections. So it's like 10 to the minus 47 centimeters squared. So there's experiments will set limits where these dotted lines are, so current generation stuff, and people are interested in going in this direction. And so we're very sensitive here, and like I said, this line is rising like this just because it's less particles in dark matter, and this line is rising like this because the experiments have thresholds. And the energy deposition from the dark matter particle scattering off whatever standard model nucleus you have becomes smaller and smaller. At some stage, you just can't resolve the experiment, and you just lose sensitivity, and that's causing this weird Okay? So I'm interested sort of in what key milestone, and these are where you might get in about 5 to 10 years, and this is like futuristic, optimistic, unrealistic, depending on your opinion. What's setting all these lines here is basically shown in a zoom in this part, in the sensitivity collaboration, or dirt detection collaboration. And the point is that interesting for this talk is that all of these current limits, these different experimental collaborations, are driven by utilizing experiments that we already have and a better understanding of atomic physics, basically, with this thing called the Migdal effect, okay? Which is a rare process in atomic physics, which is the following. So the Migdal effect is where you have a nuclear scattering, so dark matter or something comes in and scatters off the nucleus, and then the nucleus will recoil, and then the electron cloud will sort of go and catch up with the nucleus, and as it does so, an electron or electrons can become excited or ionized. So it goes back, the idea goes back. And so this is like the definition basically of this thing. So ionization or excitation of the electron or electrons following a nuclear recoil.
And what was Migdal interested in 39?
Well, I think the original way he was framing it was in terms of neutrons. He was thinking about dark matter.
Yes.
Which were recently discovered. And that's like, you can do it for hydrogen. So that efficiency. And the dark matter community, in particular with this little foundation paper with eBay in 2017, has become very interested in using this as a means to probe light dark matter. And the reason is, if this is very, very light, imagine it's much lighter than this nuclear recoil will be quite small in energy. Ping pong bowling ball is the usual analogy. But if even with that small energy position, if you ionize an electron, well, the ratio of the electron mass to the nuclear mass is very small, the inverse one is very large, and so this electron could be relatively energetic. And so although the nuclear recoil could be below the threshold of your experiment, the electron could be detectable. Okay? So even though the probability of this occurring is quite small, if it's a question of your sensitivity being 0 versus it being epsilon, you take the epsilon. And that's what's actually driving all the sensitivity in this low mass range at the moment. So I'll talk a bit about this. But what motivated us partly to do the calculations I'm going to tell about is that the experimentalists, they like to do calibrations to validate their experiments. And they're setting limits at the moment based on theoretical calculations, but no one has actually observed the Migdal effect, not from dark matter, but from anything. And so normally, in the direct detection regime, they build these nice, very sensitive experiments, and they calibrate the response to them by putting in sources in. Right? You can put in the gamma ray source in there, you can put in alpha, put in the beta ray source. And you calibrate your electron detector response because you know that you have an electron pinging around in there, and so you know what that looks like. So no one really knows. This should look like an electron. That's fine. But what they like to do is sort of have some neutron scattering experiments to be able to calibrate experiments, and also just to discover this Migdal effect. Because since the Migdal proposal, it's not been directly measured at all. People just haven't really done the neutron experiments.
So even with gamma rays?
The problem with gamma rays is they interact with electrons. Yeah. So you just scatter directly into an electron.
Very little momentum.
Yeah.
Not energy,
So you fire in gamma rays, you photoionize, and then you have no real way of distinguishing it. So yeah, they would like to do it with neutrons for that reason, and also I think the dark matter people don't get to discover things so far, and so if they could discover the Migdal effect, that would be like really nice.
Sorry, so what would be your ideal nucleus here? Would you want to go with something that has?
Yeah, good. So I'll come to this at the end. Obviously, your ideal nucleus has the mass closest to the dark matter. So if you want to do light dark matter, you want to kinematically match this to the dark matter mass. So ideally, you would build a giant detector out of hydrogen. Right? And hydrogen has issues. And I'll come to talk about this a bit at the end, how you might be able to do something. Okay, so how do we calculate it? Now we sort of leave part of the physics behind, in a sense. The classical calculation of this is you say, if I imagine myself in the nucleus, and I've just been scattered, the electron cloud looks like it's boosted in the rest frame of the nucleus. Okay, so to get the electron cloud, the electronic wave function of the boosted nucleus, I just take my ground state wave function. So this is psi is the electronic wave function of the atom, part of the orbital solar design. And I just boost it with a Galilean booster. Right? It's certainly Galilean because because we know the dark matter velocity is something like 10⁻³, or it would not be in this nucleus. So you boost the initial state, and this is so now the boosted ground state of the atom. And then you say, well, what's the final state? The final state will be something like an electronic wave function for your atom where you have some electrons in excited states or some in the continuum or whatever you define. And then it's just quantum mechanics, so you form the matrix, the amplitude, and not square. Probability, so the sub V here is for a specific angular velocity. The probability to go from initial state I to initial state F is just the mod squared of this matrix element. Basically then, the whole problem to some extent is how you calculate this matrix element for an n electron object with its exponential operator. Okay. I'm going to be talking about atoms today. There's been some work on molecules, which is what we wanted to think about initially, because molecules are. And some work on semiconductors as well, which is like a different formalism because you have non-localized bands and all this kind of stuff. Okay, so we're just going to go through now how one would calculate this. So the standard way, done by eBay, is to use the dipole approximation. Right? So you basically take this exponential and you just expand it out to linear order. So now it's 1 plus, it's like a small velocity thing, but really it's like the whole thing is required to be small. And then you sandwich that in between psi I and psi f. So what happens with the 1? Well, if you make sure that your wave functions are all correctly orthonormalized, the 1 only contributes it to psi I is equal to psi f, so that would just be a ground state transition, so not very interesting. So otherwise, then, you're only going to get non-zero matrix elements if you have single electron matrix elements, basically, because you have a single R here. So imagine that this thing is a product wave function or something like that, 10 electrons, for example. You need to have, because this is a product wave function as well, 9 would have to be equal to each other, and then you have this kind of you only get single excitations or ionizations from the dipole approximation. You need to have more powers of R to get non-zero matrix elements, to get more ionizations or excitations. So this is how we use to calculate, between just single orbitals. This is the dipole operator, it's the same you get just from thinking about electric fields. But you pay this price that you only get these things happening, and you also know, for example, when you take 1 squared of this, it is proportional to b squared. Okay? So one thing we wanted to do was understand how to go beyond this type of approximation. Okay? So what I'd like to tell you about today is how we use relativistic direct Hartree-Fock theory, which is like a standard method in relativistic atomic physics, to do calculations beyond the dipole approximation. And this allowed us to do calculations and predictions and understand really for the first time multiple ionization and excitation effects, the Migdal effect. I can tell you now this will not be really relevant for dark matter because the velocity is low, but it will be relevant for neutron scattering experiments which are ongoing. And then at the end, I'll come back basically to Venus's point and say, make some predictions for hydrogen experiments, right? So you're not going to, no one is proposing to make a big experiment out of hydrogen, but there is an idea that you could take some of the large liquid noble gas ones and just dope, just pour in a little bit of hydrogen at the top, basically. Percent level amounts. But these detectors are multi-ton detectors, and so that can still give you quite a lot of hydrogen. Okay, so how do we calculate these matrix elements? Well, the electronic wave function here is, it's not actually a product. These things are fermions, you have to anti-symmetrize. So electronic wave function is like a Slater determinant. You go back to undergraduate atomic physics of single electron orbitals, right? So now, these things here are single electron orbitals, they have some quantum numbers of AI, generically speaking. And so these people who are atomic physicists, Migdal effect comes into vogue about every 10 or 15 years in atomic physics. And so they said, well, you can make a matrix, an invariant matrix, just by forming all these single electron amplitudes, basically. And then you can make that into a big matrix, and you take this thing is then just the determinant of that matrix. And you can show that the probability then of going from psi I to psi f is just the determinant of n and jacket. Okay? So you just calculate these single electron matrix elements, put them together in a big matrix, take a determinant, and that's it basically. And that's an exclusive transition probability in the sense that you're going to a specific final space. Okay? Now, in reality, if you want to do a really good job, atomic wave functions are a bit more complicated. There's something called configuration state functions, which are like sums of Slater determinants. That's something that we thought about and included, and I won't talk about it anymore because it's not super important for this audience. That's on purpose. Yeah, okay, that's good. Okay. So now basically you know that if you can make this matrix, then you're good. Okay, so you still need to know how to calculate this matrix. Okay. And to do that, you need to know how do I make single electron wave functions and how do I calculate the matrix. Okay, so the single electron wave function part is a solved problem in atomic physics, let's say, right? Atomic physicists know how to do this. You can do it in the full relativistic regime, where these wave functions are relativistic quantum mechanics, where these things are Dirac spinors. And there are codes to do this. And if you collaborate with an atomic theorist, then you're likely to also choose. So sort of let's call it sort of state of the art, is to do this thing called multi-configuration Dirac. This means you have multiple Slater determinants, like I said before, and this means that you're doing a variational thing which is relativistic. I'm not going to go into the details of this because it's not so important. Okay. Our treatment improves upon the previous treatment in the exchange potential in particular. So when we compare with the previous work of eBay and its difference, we believe this is because we've done a better job and not just because we've done two different calculations. It's an important thing to try and communicate to experimentalists. And in order to cross-check our results, because it's relatively complicated to do, we did it twice. We did it twice in two independent ways with two different codes. Okay, so the first one is we used a package called graph, implemented with another package called ratchet. This stands for General Relativistic Atomic Something Program. It's not general relativistic, it's relativistic and it's general.
General relativistic
Yes.
actually is almost
Okay, so that solves these Dirac-Fock equations with some integrated differential equations, and it solves them with some finite difference method. Okay. And that gives you all the ground states and excited states, and this is an extension package, and that will do the continuum. Right, so you have all the discrete states and you have the continuum states. So we do that, and then we use a different package, which Harry Klein wrote, called Bertha. And the idea of Bertha is you solve these things by expansion of the wave functions in a basis set. So you know your wave function, you just pick a good basis set for your wave functions, and then solving the Dirac-Fock equation is just going to set the coefficient in front of each of this basis set of functions. Okay, and so relativistic people like to use things called G-spinors. The G stands for Gaussian. So these things are basically, you have a Dirac-4 spinor, which is your wave function for the electron. It's got a small component and a large component in the way that we do know, these P and these Qs. These things are expanded up to some order in terms of these functions, and these functions are basically Gaussians times a column. These things obviously then sort of converge quite nicely. And the reason that you particularly like these ones is because when you write matrix elements in terms of these G-spinors, all the matrix elements, the radial matrix elements that you get, can be written in terms of confluent hypergeometric functions. Okay, so that's the reason we do that. So these are totally independent codes using independent methods of solving the Okay, so that sort of ticks the first box. Now you know how to write down electronic wave functions.
So, and this, what the two independent ones were?
So this GRASP thing is a software package.
Oh, that's a software package.
Yeah,
But you didn't tell
so
us.
GRASP is a software
You didn't
package.
tell us what we did to it.
Oh yeah. It's a I mean, it's a black box for this talk, but it's a software package that solves the HydroX equations and spits out electronic wave functions. And Bertha is another software package that does the same thing and spits out electronic wave functions. And they're written by different people and they use different methods. Okay, so that basically solves the problem of getting these states. How do you now calculate this thing? Well, basically, these wave functions are these guys. So now we've solved for this, for these P's, in terms of the radial and angular parts. And the standard method then to use is to take this exponential and you do a spherical tensor expansion of the exponential. This is a sort of usual thing in the class. So then this becomes a sum over active dimension quantum numbers of Bessel function times spherical numbers. Okay. And then you just put everything together, do integrals, you have numbers times this sum of the sum order times spherical harmonics, that's fine, you know what that is. All the angular stuff gets packaged together into this thing, D here, it's the angular coefficient. And by the magic of Wigner-Ehrhart, that just reduces to 3J symbols. It's also like a solve. And then the thing you have to do is this radial, what you see is the product of the radial parts of the wave functions, which were provided by these software codes, times Bessel function. And then you spend a while doing that, and then that gives you this probability. That gives you the matrix elements, and then you get the probability. Okay? So that's all the atomic theory that we need. Okay? So now we can sort of look at, in terms of the electron energy, of the emitted electron. This is the differential probability. So this is dPV, so this is the differential probability. So we're comparing here for xenon, because xenon is used by a lot of these experiments that are excitation experiments, for a fixed electron velocity, because we're comparing with these guys, and that's what they did. This is close to the dark matter velocity, basically. The dark matter velocity is something like 10 to the minus 3, so it's a big 10 to the minus 4, so reasonably. And our answer, our calculations agreeing with theirs pretty well. So,
I missed how you know the dark matter velocity.
well, you can sort of do a calculation based on isothermal spheres and modeling, and body simulations will tell you that. You know it's an upper bound because if it's larger than that, it's larger than the escape velocity of the Milky Way. Okay, right, so the dark matter velocity distribution looks something like a truncated Maxwell-Boltzmann distribution.
Yes, certainly I realize it's trapped. So
yeah, so once you know it's trapped, that lets you roughly say that. Yeah.
So it's really just coming from the fact that it's trapped. That's you're saying.
It's coming from the fact that it's trapped plus
And
body
distance from the
simulations
center.
telling you that it's isothermal, that it's like an isothermal sphere basically.
Okay.
Right. So it's the trapping gives you the truncation and the fact that you believe it's, unless it's doing things like more complicated things like self-interactions, that kind of thing, tells you that it's basically isothermal. And then that tells you that it's Maxwell-Boltzmann, and then
I have to.
okay. So this is the ratio between our calculations and these other calculations. There's some squiggly stuff, but that's basically just where you have a sort of a difference in orbital energy that comes in. It's also sort of important because, as I said, experiments have thresholds, and the order of magnitude number for an experimental threshold on electron detection that you should have in your head is about 1 kilo. So anything to the left of this line is sort of good. Okay, so anything to the right of this line would be very well. So for dark matter, all the fancy calculations we did are not tremendously important. Okay, that's not super surprising. The dipole approximation is a small v expansion, and you're just at small v for dark matter. But because we can do, we can do this calculation and make this nice matrix, we can make predictions for multiple transitions that hasn't been possible before. So helium is a nice example. Look at this because you can solve the system with only 2 electrons. Well, here's the nuclear recoil velocity V, it's in units of alpha, which is the right units for atomic physics. And this is the probability of something to happen. Okay, so if we start at low recoil velocity, this is a zero emission probability, so that's a ground state transition. Okay, so at low velocities, you don't have ions. You can have a single ionization, and that's this blue curve. And down here, this is proportional to V squared. This is rather than. As you increase the nuclear recoil velocity, you have a larger probability of having double emission. Right? So if you come to higher recoil velocities, you can have double ionization or excitation. The difference between the solid line and the dashed is double ionization or is there excitation.
Why are they so close?
Which?
The double emission versus single emission.
Why are they
The
so
solid line is the single emission.
The blue.
Oh, sorry,
This is single ionization, and this is single excitation.
I missed it. What's the difference between the dotted line and the dashed line then? They're torque.
This one and these 2 lines?
Yeah.
This is the double ionization, and the other one is the double transition. So if you have 2 free electrons, your 2 electrons coming off, are they both in the continuum, or is one in an excited state and one in the continuum?
Okay.
And so as you increase the recoil velocity, the probability of just having a single transition or excitation is low, and it's very, very likely that you're just going to double excitation. What is happening here, hit the nucleus hard enough that in some sense it just flies out of the atom. Electrons are just yes. Okay, since it's helium, there's only 2 electrons in the game, so if you add together the probability of nothing happening plus 1 thing happening plus 2 things happening, then you get 1. Now, we can't do it for arbitrary numbers of electrons, basically for computational reasons. We can go up to sort of triples, and maybe quadruples if you spend a lot of time. And the way that this manifests itself is looks like a loss of unitarity. Right? So this is for neon, where you have more electrons than 2, but more electrons than 3 is the important one really. So we can do singles, doubles, and triples, but as you increase their velocity, you should have to include quadruples and quintuples and stuff like that. So
This is determined by the size of your determinant. Is that what it is? Your determinant.
that we can't do the calculation, you mean? Or
Well, no,
it's just a combinatoric problem.
It's a combinatoric.
Well, it depends what you think the problem is.
The
What do you want?
determinant, the
Sorry.
determinant is determined by how many electrons you're going to consider.
Yeah.
So, and what is the obstruction to
Doing more.
doing more?
Not the size of the determinant, but the combinatorics that goes into it. If there's only one excitation, then it's just like 10C1 or something like
Yeah.
that, which is smaller than 10C4 in some sense. Right? So there's much more combinatorics that go into having a quadruple excitation, a quadruple transition than a single transition. In terms of all the things you have to calculate.
Yeah, just think that would have expected a lot of the factors of just weights from that combinatorics.
What do you mean by weights?
Just partition, how many many of the transition have the same conjugacy class.
I don't know if we see that in the way that you solve it though, if you're just doing it numerically. In the end, it'll turn out that you probably don't have to do this. So it looks like at high velocity that you have a loss of unitarity. What this plot is also showing, the difference here, the ratio, is the ratio, so this is dotted and dashed now as well, but it wasn't the previous page, which I thought was for. But the solid is the Bertha calculation, code A if you like. And the dashed one is the other calculation, right? And this is the ratio, so we have percent of agreement between our two calculations. So we're pretty sure we've either done it right or we've done it wrong in the same way, which is best logic. Okay. Now, do you have to worry about being out here in experiments that we're going to do? You probably don't, basically. The other thing is, obviously, as you increase the nuclear recoil velocity, the nuclear recoil energy, at some stage, if you're actually firing neutrons at a nucleus, you should worry about nuclear physics at some stage. That you don't just recoil the nucleus, that actually you fission it or something like that. There's other things going on. Okay. So if we look at these multiple transitions of physics, well, you can kind of guess by looking at what the single transition, the original plot, the first plot that I showed you looks like in terms of the electron energy. So you're more likely to have a low energy transition than a high energy transition. And the high energy transitions are dominated by inertials, the low energy ones in the inertials. So if I treat the probability of making a multiple transition as a product of probabilities of single ones, which is approximately correct, you're very unlikely to have a multiple transition that gives you multiple hard electrons. Much more likely to have one hard and one soft. And that's basically right if you go on here, go through the mechanics level calculation, looking here at what are the probabilities of transitions for the resolution of pairs of orbitals. You're much more likely to get dominated by one S2P, so you get something from an inner shell and something from an outer shell. You get one hard electron, you get one soft electron. That soft electron is probably going to be below your threshold. Right, so at large recoil velocities, where the experiments are perhaps going to be, some of them will be operating. The observable rate, right, if we include thresholds again now, so now we do a calculation again. This is a complicated plot. We'll go through it. The observable rate is dominated by one hard plus multiple n soft electrons which are below the threshold. Okay? You're not going to see these things. So this is now recoil velocity versus probability, where we put a minimum energy, so there's a threshold. So the blue here is we have one hard electron, so this is a single transition, which goes away like this. And then we can do two other calculations. One is where I have a double emission where I have both above the threshold, so two hard electrons, and a double emission where I have one hard and one soft. You can see there's an orders of magnitude difference between these two things. So you're like, many orders of magnitude more likely to have one hard and one soft, or one hard and multiple soft electrons. So although you go to the trouble of doing these calculations, to do multiple ionization calculations, etc., what you're going to observe is just a different rate for having one electron coming out, because the other ones will be sub-threshold. So we thought about that and then decided that the right sort of thing to actually calculate was what we call semi-acoustic probability. Right? So the probability of having one ionization electron above threshold and the other one's being soft. So the probability to make a transition from the initial state to a final state where you have one guy, can't be one, this is a single electron orbital, which is hard, and some number of soft things, okay, which you write out into matrix elements as you do a sum over the n minus 1 other electrons, where their energy is below the threshold. And the idea is that you can simplify this in a certain way, okay? So the probability of producing multiple hard electrons is very, very small. So it's a good approximation in this sum to replace B less than some threshold with B less than infinity. So rather than just doing a sum over these particular states, you do the sum over all states. The error is something like the ratio between these two points. So in other words, this is like the correct observable definition, but in functional terms, you can do it this way, where you ask the probability to go from this state to one ionized electron, summing over everything else. And once you're summing over all states, that's going to let us simplify things, because then we can use completeness relations with the n minus 1 other electrons. Okay? So this probability is mod squared of the amplitudes. Now I have sum over all states, soft things, and then I have this guy here. If I have a sum over all states of this outer product, that just gives me one probable states. So all this stuff must go away, and it turns out that this observable probability is basically given by this quite compact, relatively simple function. And so it becomes a sum of now the single electron matrix elements. Right? So you do a sum of the initial state, you do some final state, and you just sum of the probabilities. And this is actually reasonably straightforward. It's easier in a sense to calculate. So there's an assumption, of course, which is that the probability to produce multiple hard electrons is small. Some states it will break down. You can estimate when it breaks down. It breaks down when V over alpha is order 9. And that's up here somewhere. And that's a number which is larger than you're going to achieve in any experiment people are proposing, unless you fire very relativistic neutrons at helium, which people might do. Okay, so the approximation we make is probably going to be pretty good, except maybe for helium. For helium, you probably don't even need to make the approximation, because you've only got 2 electrons in the first place, so it won't matter too much. Okay? So now we're pretty confident that we can predict the things that we would like to predict to experimentalists in order to actually make observations. So let's talk about some applications in terms of physics. Oh, that doesn't seem right. Oh, no, it is right, okay. Should I shoot to finish on time, or can I go?
No, we will relax.
Okay. So the first application is in terms of dark matter excitation. And I'll just focus here for a couple of slides on these little element detectors. So this is the XLZD experiment. I'm not a member of any of these, by the way. The idea here is that you have a few tons of liquid xenon here inside what's called a dual-phase TPC, so dual-phase time projection chamber. Nearly all of the liquid xenon, there's a little bit of gas at the top, basically. And so if dark matter comes in and scatters, it will liberate. So this is, you end up in an excited state. The dynamics of this is actually quite complicated. You scatter off the xenon, you actually form a xenon Xe2 hexamer, and they bind together, and then that decays, and that gives you photons. That gives you UV photons, 148 nanometers. And then the whole thing is surrounded by PMTs. This is all reflective walls. And then the top and bottom is 500 PMTs, photomultiplier tubes. Okay. So you can detect these photons. It will also, when the xenon atom that you hit is pinging around, it will liberate some electrons in the surrounding ones. The whole experiment sits inside an electric field. So then those electrons get drifted up to the top. They'll cascade even more electrons in the gas phase, that's what it's there for. And then you can detect those electrons as well. Okay, so you have 2 signals, you have the photons and you have the electrons. And the nice thing is, this dense array of PMTs gives you an X and Y direction, good idea of where the thing occurred. And the time difference between the photon and the electron signal is telling you in Z what you are. So you basically have a 3D reconstruction of this thing. And the numbers of photons versus electrons can also tell you something about what kind of scattering you had. Was it a nuclear scattering? Was it an electron scattering? So these are a well-developed industry, let's say. Okay. So we can make predictions for these guys, right, in terms of observable event rates. I can talk about those detectors are great now, but it's not so important. So this is now like actual, not just probabilities, it's an observable rate, right? So it's a differential event rate in terms of recoil energy and electron energy. So there's some kinematics that goes in terms of the mass number and scattering cross section, reduced masses. This is the nuclear form factor. This is the stuff that we have. This guy G high is packaging all the stuff about the dark matter velocity. Okay. So observable rates are pretty small. This is in kilograms per year per kd. Right. So in terms of the observable electronic energy, you're not getting events per day. You just get a few scattering cross section, which is roughly what we're doing. Okay. So we compare with eBay, the agreement is sort of 20% or something like that. So, I would say this sort of means that the derived limits are relatively robust doing our improved calculations, and the difference is something like 20%. So it's not so important, all this fancy relativistic stuff that I've told you about. What's much more, an arena where it's much more important is all these experiments that are currently happening, which I know is 3 on neutron scattering. Okay. So the idea for these experiments is you get either a dark matter detector or you just build a new detector out of something and you fire neutrons at it. Okay. So neutron sources are something you can get now. You get the DD and DT neutron generators. This is deuterium, deuterium, and deuterium tritium. These are little fusion sources. And they emit neutrons. They emit pretty high neutron flux. Right? So the cartoon of these experiments is you have a neutron generator, and you can get these things, and you get like 10 to the 9 or 10 to the 10 neutrons per second of either 2.5 MeV or 15. And then fire those things at some interaction volume, neutrons come in, light off something, get the nucleus coming out, and you get, say, 1 higher electron. This is soft electrons as well. The main experiment we're currently going to talk about is called Migdal. This stands for something. The M stands for Migdal. So like a dark matter laboratory or something like that. And that's an optical time projection chamber. So they have a camera pointing down. They have this sort of grid thing as well. And they have a camera pointing down. And the cool thing is, this is simulation, this is in beta, so they can image if something happens, the nuclear recoil and the electric recoil. So they can see both. And really just like see the actual, as it is moving, it causes scintillation. So they can see it forecast which they happen there, and then they can actually image the tracks. These are like millimeter long time things. Okay. So if you are actually having Migdal events, they can literally, in a sense, just see it. They can see the nuclear and the electron at the same time. And that's not true. The electron threshold is a little bit higher than some of the dark matter experiments, but if you look at the rate, so if you take our sort of probability predictions and fold it in with other stuff, the rates are high, right? So this is from using our results in their white paper, which we had basically at the same time. They weren't, this is before they've done the experiment, so it depends on what their track resolution is, what their electron energy range is. It's a few kV. You're expecting basically like dozens of events per day. They also reckon that because they have such good imaging, the background is under control. So background is like a large, depending on which kind of neutrons you're using, like not much smaller than we're seeing. So if it works, you should be seeing hundreds and hundreds of Migdal events, or thousands if you run it for a long time, very, very small backgrounds. Okay? So in order to get predicted rates for these experiments, it's the same kind of idea as for the dark matter. So the differential event rate is the neutron flux, which you know from fire or whatever, number of target atoms in your detector, neutron nucleus cross section, d sigma dd. This is something you can look up. There's libraries for this, times the probabilities that we've had. Okay? So then we're able to make these kind of plots where you sort of have nuclear recoil energy, differential cross section for all the different kind of stuff that you're running. Initially, you'll see it 4, this nice scintillator property, and then if that sort of works, they have plans to run different kinds of elements which are relevant for the direct detection program. Okay. These are relatively high energy neutrons, 2.5 MeV, 15 MeV. So you're not really kinematically in the regime directly relevant for dark matter, where you have much smaller velocities. So that means you have to include like elastic and inelastic transitions in the nucleus and stuff. And this causes the event rate, the differential event rate to and all these things just stop at some stage because the neutron energy is fixed. You can't have a nuclear recoil energy that's larger depending on neutron energies. Okay. One thing that I have to say is that initially when we went in, we wanted to make predictions for CA4 and do it for molecules, but that's really, really hard, it turns out. So we treated CA4 as C plus 4F. So our molecules are just atoms. Now, one reason that that shouldn't trouble you is that the observable electrons, those hard electrons, are coming from inner shells. And those inner shells are not going to be affected by binding stuff. They're not going to be hybridized or anything like that, so you shouldn't worry about it too much. One reason you might worry about it a little bit is because there is still a molecule there, and in terms of differential stuff, you would imagine that you're much less likely to emit an electron. If you imagine you scatter off the central carbon atom, you'd say, well, it's probably unlikely that I'm going to emit an electron directly into one of those fluids. Right? It has to come out somehow. So there might be some differential information in there that could be important that we don't have. But we don't know until we have data.
So this Migdal experiment, they started taking data?
Yeah, they got data. Yeah.
And I have not seen it.
No, I'll tell you. Yeah, I'll tell you. Well, in a sec, I'll tell you in a sec where they're at. Yeah. Or I'll tell you where everybody's at, basically. Yeah. Okay. So once you take our predictions, you fold it in with all this stuff, and you do this semi-inclusive calculation. I think these are doing quite relativistic things. These would be different event rates. This is events per day. And it has this weird looking shape because the neutron nucleus cross sections have some quite complicated shapes. So firstly, that's because of neutron nucleus stuff. Secondly, if you're just doing this calculation where you can only do single ionization calculations that people could do before us, the difference between that, this blue dash line, and the semi-inclusive calculation, which I'm telling you is the right one, is large. Right? So this matters for the neutron. It doesn't matter so much for the dark matter experiments, but for the neutron scattering experiments, you have to do this. It matters. Okay, and for helium, which is always sort of our poster child in a sense, with helium you can compare the semi-inclusive calculation, which is approximate, with the sum of the exclusive things, and you get percent. So the approximation that you could make, that you don't have to in this case, because you can do the approximation and the exact calculation of helium, it's a good approximation of it. And helium is the worst case that you could have. Okay, so Migdal status, this is events per day, where you expect to have hundreds of events. Analysis ongoing, basically. They've done a couple of runs. They did one last year, one at Christmas, and one that's done. They've had a bit of difficulty with their neutron sources. They keep breaking. And then when it breaks, they have to send it back to America to get fixed. And that takes time. Last I heard was that they were hoping to have some results for the summer. I don't know if they'll have like sensitivity to the actual Migdal effect, or if there'll be more like kind of calibration papers or something like that. But a few months ago, they were saying, well, we'd like to have something for the summer conferences. I don't know if that's happening. So they don't have any results yet. Okay.
This one was with helium.
They're running initially with CF4.
CF4.
And then they're going, if they get good, once they sort of, if they can tick that box, then they'll go on and do helium and xenon and argon and all the other stuff as well.
So why are they running with
because it's a scintillator, and it seems like the best thing they can run with that will give them the best tracks. So from the perspective of the direct detection program, you don't care about it very much. But I think for them, for just doing like experimentally, they want to run with CF4 first because it will give them the best tracks in their optical time prediction channel. Yeah.
And I didn't fully grasp why you were able to get away with just treating the carbon and you were ignoring the...
Oh, we don't know. Well, I don't know if we're able to get away with it yet until we have data, in a sense.
What was your argument that you could ignore?
That we could.
Yeah.
That we could ignore the fact that it's a molecule. Is that
the fact that it's a molecule seems reasonable, but I thought you were ignoring as well the fact that you were treating the fluorine differently.
Well, we're just treating it as a bunch of atoms. We're saying that CF4 is 1 atom of carbon and 4 atoms of fluorine. And our predictions for the event rates are based on that assumption. Right, so any kind of molecular dynamics is being ignored in that sense.
It's dense enough that you don't need to worry about the relative density of the fact that the 4 are fluorine are clustered near the carbon.
So so that's the reason that you might think that you should take into account that it's a molecule. That if you did, say that you had a Migdal event where you scattered off the carbon nucleus and you emitted a hard electron from the carbon K shell or something like that.
Yes.
Our assumption is it's just an atom of carbon and it just emits this thing. Okay, that's the atomic assumption, but it's in a molecule, so there is fluorine up there and there and there and there, and so you might think, well, it's quite unlikely that that electron will get emitted directly towards the carbon atom versus out that direction.
Yes,
so there's some that we don't and can't take into account. We talked about it a bit and then decided we wouldn't do anything about it until there was data and we knew it was important to think about.
Except that the fluorine atom isn't point-like as far as the electron is concerned. But you're saying it's relativistic enough that you...
Oh, we're not even making an assumption about point-like. I'm just saying that once it is a molecule, you just imagine, even if it was just like two things, you just imagine that you're just less likely to emit towards the thing it's bound to than in the other direction. And from that perspective, taking into account the fact that this molecule could be important for getting the correct rate.
Yes.
But how much, we're not sure because we haven't tried to account for it yet without having data. From the calculations we've done, we can do some angular differential stuff just for atoms. So we might, once they have data to compare to, we might do some more stuff on the differential side. So who else has been doing experiments? There has been an experiment who have written a paper. This is at Lawrence Livermore National Laboratory in the US, the dark matter people. So they got one of these DT sources, relativistic neutrons, and they built a new small xenon time projection chamber, this big. And they just do this thing where they have the source here, you surround it with shielding, fire towards this xenon time projection chamber, so you can measure the events in the time projection chamber. And then you have a bunch of neutron detectors behind it, so you can detect neutrons as well. So they ran for some amount of time. They used not our calculations to do this prediction, but ours doesn't really substantially disagree in any important sense for this. And so they predicted that it would run at 150 Migdal. So that's this one. So this is differential. This is the number of detected electrons. There's 2 electrons. And this is physics returns. So there's a very large background here. We just have single scatters pouring neutrons into your detectors. So you can get a lot of stuff from this neutrons single scattering. And the neutrons are coming from that recoil of that xenon atom crashing into all those atoms, not from the recoil. So we look over here, and that's your signal should be living over here. They expected 150 and they got 16. Okay? This is quite mysterious. They don't know why this is the case. Of course, it's possible that the calculations are totally wrong. I don't think that's the case. I think the calculations are relatively robust.
But xenon should be easier, shouldn't it?
Okay, good. Yeah, so xenon is easier because it's not a molecule, but it is a liquid.
What difference does it make?
So it could be important because it's sort of
As long as forces there.
So if you make this electron and it's in a liquid environment, then there could be things going on like electron-ion recombination, which we just don't see. No one really knows how to calculate that kind of stuff. Where that's the electron just doesn't get very far. Something like that. It's sort of blocked in its propagation by other close by xenon atoms, and then it recombines relatively quickly, and so you don't get Migdal effects being out here. We have many electrons, the Migdal effects are living more in here, and it's just going in the background. So there could be some quite complicated liquid phase xenon dynamics that's going on that is not taken into account in our calculations and not in any
Don't they have to worry about how much the fiducial volume?
Volume? Well, not for this thing. I mean, they would take that into account. Yeah, because it's a TPC, they know where each event is coming from within the TPC. Okay. So the idea here is that this might give you fewer electrons than you Migdal effect event than you think, and so the Migdal effect observed will not be living out here, it lives in here, and that sits underneath this very, very large background. But so this might cause you concern from the perspective of dark matter searches that people have been doing. But there's an argument that this shouldn't be such an issue for dark matter searches, which is that the reason they have an enormous background here of this stuff is because they're firing this many neutrons at their detector. They're firing 10 to the 9 or 10 to the 10 neutrons per second into their detector. When you're doing a dark matter experiment, that's not what you do. Right? You want that detector to be as quiet as possible, and essentially to have zero other stuff going on. So from the perspective of an actual dark matter detector, even if there's some complicated dynamics going on that no one understands yet, that shifts the signal from here down to here, this peak doesn't exist. Because this is because the size of this thing, that ratio is because you're firing so many strongly interacting neutrons into your detector. And so in an actual dark matter experiment, this wouldn't be there. And so even if this guy out here moved down to here, that would still be within your signal region. Right? So
what is that signal to background ratio?
If it's out here, it's not too bad. It's like, because this is a simulation, so you have fractional events, right? So like that's one event, so it's up here.
The noise is up there, so you
Noise, but here you have
10 events versus 10 to the 4.
here is like 10 events versus 10 to 4.
Yeah.
So here you're good. But if you're not firing neutrons in your detector, then this is up down here somewhere.
Yeah, no, I understand. So presumably the problem is that they haven't got precise enough control over the background. That's the
In this
detect.
experiment. Well, it depends on what I mean, they can't stop this.
No, I know, but you need to subtract it off to get your 148.
Well, if this thing weren't happening, you wouldn't, because you could just like make a cut here and just count the events over here.
But that's not down to their experiment.
Well, it doesn't seem to be happening. What do you mean it's not
They're
happening?
not cutting it off there, are they?
Pardon?
They are not cutting. Their experiment is not in that regime.
Well, this is their data.
Yeah.
Yeah.
So they have to subtract off that peak, and when you.
I know, well, you don't, right? You just sort of say, I only count events where I have more than 100 electrons.
Oh, I see it.
And then you know that you're just like, you don't have to subtract, which goes you like awful systematics.
Well, you still have to subtract.
So look out here, what you have an estimate of what your background is out here, and you're mostly.
But you're saying the background is only factor 10 larger there, but I still need to be able to control this.
You still need,
I need precise
You need precise, if that,
analysis of the background in that
that I
region.
totally agree with. Yeah. And they have, gone and tried to do that in the paper with arguments about, you can have single scattering, but because it's neutrons which are strongly interacting, you can also have the neutrons can like scatter multiple times in your detector, start with them blue, that's something more around other things happening, gold passive scattering. But obviously, the background dynamics is again more complicated than in a dirt detection experiment.
Very
Because you're firing against
I would think that if you can't do it in the main event there, the complications are probably as much.
It depends,
Because you're going out into the tails of the district.
You are going to the tails of it. Yeah, so there's that argument as well. Yeah. So this is, I don't know. No one, it's still not, this is like a year ago. I'm not sure why this is the case, but it means that doing these kind of experiments without adding neutrons might be more difficult or not as appropriate as people previously thought. Can you go to lower neutron energies? In principle, you can. You use one of these things and you just put like something like, blocks in front of it, right? And then you just like filter. It's called a filter, but it's like a bunch of blocks. And then that just, from scattering, will filter the neutron energies down to small, to lower some MeV or something like that. Because you're just like doing that by scattering, you lose in flux. So you can get to lower neutron energies, but you also then you take a hit in the flux, and so you take a hit in the event rate. So there's no free lunch in this movie.
And then define their S1, S2, is it set up like LC?
Yeah. It's also it's a smaller LZ effect that they built. Okay. So they see nothing. And then on LZ have also done something. but they haven't published it, so I don't quite know what's going on there. So LZ actually has a tube. There's a tube that goes, LZ is one of these experiments. It's an actual dark matter experiment, like a ton-scale dark matter experiment. There's a tube that goes into LZ, which they can put for, which is for putting sources into. And so they started firing neutrons down this tube. Okay. So they did this, and they had a low flux filtering. And now, this is some slides from a talk at a conference last year. And so they have a similar idea, so they've done some S1, S2 analysis, basically. This is the photons versus electrons, basically. And what they find is that they have seen 23 events. Their background model predicted 10. This is a 3.5 discrepancy. So when I saw this, I was excited. And then they have provided sort of no update since. Now, I know a couple of people in LZ, and they haven't even put out like a Migdal dark matter search thing. I think they're very conservative, right? So they're very wary to publish things that they don't feel that they understand. That's probably what's going on here. And I don't know what further analysis has happened since then, but yeah. So at this stage, there's no definitive experimental things to say. Some people have seen an excess and then done nothing more about it, or not told anyone why they haven't done anything about it. And then the other experiment has seen effectively nothing, when they expected to see lots. And then the other experiment, hopefully Migdal will be the definitive one, has some technical difficulties, but I'm sure will come through in the end. Of course, it would be nice here if you could say, do it for more, but because it's actually LC, they have other things to do than fire neutrons with their detector orbit, right? So they have runs where their primary thing is looking for dark matter. I'm not sure they're actually going to do anything with this.
How much xenon does LC have?
A few tons.
There's not enough xenon in the world, I'm guessing, and they have to share with xenon and ton, don't they?
No, they don't have to share it. If they do a next detector, they'd have to share it, probably. But they wouldn't share it, they'd pool their resources. The other thing about the xenon is they don't own it. Investors own it. So they have it, which is, okay, which will lead into the next thing, which is a nice idea that maybe won't happen. Which is this HydroX idea, right? So coming back to the beginning of the talk, as to what's the best atom or best element I could have to do a Migdal thing, will be hydrogen. And so it's an idea which comes from, this is our idea, the idea does come from the foundation, which is you dope LZ with hydrogen, H2, after the main physics one, right? Because experimenters don't like to fool around stuff with their experiments, so you wait till they're into their physics run, which is like 2026, and then you put a small amount out. And that should be really, really good for searching for like dark matter. So there's some good things about that. You obviously have a larger recoil energy compared with xenon because it's really light. The details are important, but you get pretty good yields scattered on hydrogen. And there's even some like possible, there's some early, R&D data, let's call it, where like you can maybe discriminate between H2 recoil versus xenon recoil. That'd be really nice too. You can definitely dissolve hydrogen in xenon. So this is data of temperature versus mole fraction of dissolved stuff. So up here, flux, which was the predecessor of LZ, is showing to dissolve hydrogen as well, at like 50% for sure. Okay, so then on the other hand, you don't know, and there is R&D work ongoing. How does this affect your S1, S2 signal yields if you put stuff in? So what the signal yields look like? Behind the nice picture of LZ I showed you before is a giant cryogenics plant that constantly filters the xenon. It has to be very, very pure. So just putting that kind of thing. And the other thing that could be pretty critical is about tritium contamination. The xenon they have is extremely pure. You don't want there to be any trace amounts of other stuff that will cause radioactive decays inside your detector. That's just noise from your perspective. Hydrogen, if there was going to be some tritium around that causes decays in your detector, that's a source of noise, which could be quite large.
Firing neutrons into the experiment is not going to be popular either.
You could, yeah, that's you can do it. It's probably not going to transmutate anything really bad from that perspective. They know at the beginning, like when they switch, basically even at the beginning, they can see quite well actually. When they switch on the detector and the filtration plant is running, and there is impurities in there, they can see the decay curves and identify the decay curves of different impurities in there. Like they have, these detectors also have like a sort of a side hustle in doing searches for rare decays. They set some of the best limits in those things. Okay, so I will just go through this really quickly. So the idea is basically you put in, and this comes from experiments, I said, made projections on if you put in sort of 2.6% H2, which is a couple of kilograms, and imagine you have 250 live days exposure, which is like a year or 2 years, you just do it at the end. They made some assumptions, which I won't go into, but they're sort of reasonable assumptions as to how this thing might behave. Then, compared to where we are now, which is all this colored mess of lines over here, their HydroX experiment would rule out this yellow stuff. And these yellow dotted lines, all of this stuff would become ruled out. This is not some, this is the proposal to include in. This is for spin-independent scattering. Right? So you scatter spin-independent of the nucleus. You could also couple to spin and then have spin-dependent scattering. And hydrogen would be fantastic for that because it's a single spin, it's just a proton. Neon is a terrible for spin-independent scattering. And so if you did this HydroX experiment, then currently this is the current experiment here. So you'd be probing sort of orders of magnitude of space that we have to touch. And so ours, the cute thing that we did was like, that's a nice idea. If you add the Migdal effect on top of that from hydrogen, you'll have like the best limits you could possibly set. Okay, so in the interest of time, we know how to do the calculations. We treat hydrogen as H2 as 2 times H. These are basically what goes on that slide. And so if you did Migdal effect with this H2 dot xenon, you'd be able to rule out this stuff in the spin-independent case. There's 2 different lines here. It depends on how many, what's your threshold for the number of electrons that you can measure. 5 versus 3. And in spin-dependent space, you would rule out all of these. So you're pushing in terms of mass down into the 10 to MeV regime and increasing the limits some of those magnitude. So that would be really cool. And then the next thing that you could do after LZ would be what's called a G3 experiment. The current ones are called G2, generation 2. There's an idea, which is really at the proposal stage, XLZD, which is the xenon N-ton collaboration plus the LZ collaboration plus the Darwin collaboration, and they just have this material in, that's what they are at the moment. That would be like a 20-ton xenon detector. That would be like as much as you could do. This is hard because there's only so much xenon around. And it turns out one of the main source of xenon, the main xenon processing plant of the world, one of them used to be in Mariupol in the Ukraine. So xenon prices did go up quite a lot in the past few years. Investors, and one reason why this experiment, why the might not happen, is because the experimenters might want, the investors might want their xenon back. LZ got a contract for so long, and then if the investors want to buy it, if you did another experiment, and you could do another experiment, then well, I suppose it should be easier to do better. More xenon, and you just rule out all this kind of stuff. Dark sphere is another proposal for an experiment. Again, independent space, you do incredible stuff. Okay, so that's all I've got. Apologies for running over time. I won't read my conclusions. You know, these are the conclusions. Okay? So thanks very much for coming and listening to me. I've enjoyed talking to you. I've enjoyed listening to it. Thank you very much. If you want to play around, everything is in a public repository, which you can interface through Python or Mathematica or whatever it is to either do. Questions?
Do you think Panda X has any plans for laptop?
I have no idea what Panda X plans to do. Oh, in terms of doing like H2 developing or something like that? Sure.
Yeah, for laptop.
I have not heard anything. Yeah, it can be, I mean, yeah, I think it's not just in that it can be difficult to know what the Chinese experiments are going to do. Yeah. If I had to, it's not clear what if XLZD will go in. That will be sort of, they have to figure out a lot of stuff and get funding. Maybe, I think the Chinese have been talking about that there could be a Panda Super Panda, I don't know what it would be called, but something similar. So Panda X there's a Chinese experiment, which is also, let's call it a G2 experiment. It's a little bit smaller than LZ, but it's similar, sort of multi-ton. And if they want to go and do a 20-ton experiment, then it's probably what, that's sort of the short thing. I don't know if that's something that they plan on doing.
What is the timescale you would anticipate some detection of the Migdal?
Well,
optimistically?
Well, I don't know. I would hope within the next year. I've been hoping already from the Migdal experiment. But it depends on, does their neutron source break more and this kind of stuff. The other nice thing about the Migdal experiment from this perspective is they're running with gas. So compared with the other results where there might be some problems with the liquid phase or whatever, you'd hope that Migdal aren't going to have those kind of problems because they're actually doing a gas experiment. So I hope within the next year, but it's not my,
The worry is that in the liquid phase that the nuclei are too close together.
The atoms are too close together, and that just affects the electron dynamics in some complicated way. That's not a calculation I'm going to do. Whereas in the gas, I mean, I would really like it in the next year, but it's just not my goal. I would also really like it to agree with our calculations. It's not my goal either.
Do you know of other experiments aiming at non-dogmas around that region?
For Migdal sensitivity kind of stuff? For doing things with neutrons, or just?
For Migdal and then without Migdal, just non-dogmas in the range that you're looking at.
But you mean you mean experiments that will be sensitive in that part of parameter space, or experiments that will be searching for the Migdal effect using neutron? Both. Okay, so the xenon ones are doing really well, and that's kind of one of the unexpected stories, I think, of the past several years, is that people were proposing smaller scale experiments with very low thresholds in order to be sensitive in this part of parameter space. And it turns out that you can, if you have a very large experiment where these rare things can happen, the largeness wins. And so LZ haven't published a Migdal dark matter search yet, but when they do, it'll probably be better than Sensei. Sensei is a silicon experiment. They use silicon, these cool skipper CCDs things, and the CCDs themselves are basically the detectors. So they're building something out of CCDs, and they have very low thresholds, but small, right, like gram scale stuff.
If you hadn't successfully calibrated your apparatus against some known experiments, how can you be?
For the Migdal stuff? Yeah, well, you don't. That's why they want to do these experiments. So Sensei is going really well as an American experiment, and they have plans to scale up to like large scale. Well, large being like hundreds of grams or a kilogram for them. LZ will be very sensitive down there as well. And so they're going to be the main ones to watch out for. This thing called dark sphere is a different, slightly kind of proposal. It's called it's a spherical time projection change. So it's a big sphere filled with compressed gas, and it should also be able to have very low thresholds, which would be very helpful down there. That's kind of not funded at the moment. There's R&D, but they built a small one, but not a big enough one. There's an experiment which is in R&D stage, which is going to be built called Herald. That's running with superfluid helium, which again is a light nucleus. Superfluid helium comes with its own complications experimentally. They will have some results in that regime, I expect, in the next several years. How low they get in terms of their dark matter mass, I don't know. So there is quite a lot going on in that space. And there's also some crystal-based experiments as well.
So would the crystal-based one be more sensitive to Migdal effects?
It depends what you mean by more, because again, there's always a question of how much you have. Right, so the crystal ones can be quite sensitive, but they're small.
Yeah.
So saying that it's more sensitive than LZ, which is really big, like its thresholds will be lower, probably, but LZ is much, much bigger, and I think it might come out in the wash.
If we can thank you, I'll let you get into
material treatment.
So let's go back to the